All right, hey guys, welcome to the third discussion section type thing. Um, so, as with yesterday, I'd like to start off by just accepting any questions you guys might have. I hope you all saw the announcement that I made, which was about office hours. So, I will be having two office hours tomorrow, one in the morning and one like right after the um, discussion thing, which will be at 5 again. Uh, so that'll be another good place to ask questions, especially about the homework if you want. But yeah, any questions? Oh, you know what? Hold on, let me close my door. All right. I just realized it was just sitting open. I like to keep it open sometimes for the fresh air and stuff, you know. All right. Anyway, so sorry if there was like a bunch of noise coming from that, but yeah. So if you have any questions, feel free to ask.
In the homework, so are we allowed to use um, problems we've already proved in a previous problem to prove like another
Yeah,
problem?
definitely. If it's something that you've like done on like a previous homework, or sort of yeah, if I've sort of like held you responsible for a problem in any way, you're free to use the result of that, and you're actually very much encouraged to do that. Like a lot of the problems will be building on each other. So it'll be important to use stuff that we do as we go. But if it's something that you haven't done, even if it's like a problem from the textbook, then ideally you'd either find a way to justify it or not, or like find a different way to do the problem that you're trying to do.
Okay.
Yeah. Any other questions? Okay. So in that case, we can just go right ahead into the exercises that I picked out. So I tried to pick stuff that I feel like, circles around the same sort of the basic, themes of what you have to do on the homework and stuff. The first one I'd like to do is just a sort of direct proof of convergence. So uh, let's try this one. So prove, so, from the definition, so with epsilon and n, right, that uh, the sequence Sn given by 1 plus sine of n over n converges. Okay. Uh, so yeah, I guess I'll go ahead and put you guys into little groups for this, and we'll take like 10 minutes maybe to work on it. So let me do that. Yep. Okay, so let's sort of go over this now. So this is kind of an example of oh, what am I doing? Hold on. Oh yeah, here we go. So this is an example of a sequence where you can't, basically you can't solve directly for what capital N has to be, right? So let's sort of start our proof, right? It starts with, well, first, actually, the very first thing we have to do is pick a limit, right? Hopefully everyone was able to kind of look at this and more or less see without too much effort that the limit should be 0. So we claim Sn converges to 0, right? Because sine of n is just this bounded quantity. It stays between plus and minus 1, and then there's another 1. So the biggest this can get on top is just like 2, and the smallest it can get is 0. But on the bottom, you have a denominator that grows to infinity. So that's why the whole thing goes to 0. And now, now we'll say, so let epsilon be greater than 0, right? So now let's remember what our goal is. We want to pick n such that for all n greater than n, we have 1 plus sine of n over n is less than epsilon. Okay? So, like in the lecture, I kind of did an example of this where basically you kind of pretend this is almost like an equation and you just like do algebra to solve for n, like write n in terms of epsilon essentially, and then just pick whatever expression of it in terms of epsilon you get, you just pick capital N to be that. But we can't do that in this case because I mean, how are you going to invert like sine of n and stuff like that? You can't really solve for n. So what you have to do is basically do some estimation, okay? So here's how I would approach this, okay? I would notice that, well, if you just think about it, right? Like what I was describing before, it's good, really healthy to kind of like get in the habit of just thinking about like how quickly do various expressions grow? Like how big can they get and like how fast do they grow? And how can I simplify them to sort of isolate the most important behavior that they have, right? So basically in the numerator here, we have something that's bounded above by a constant, right? It ends up not mattering that that the sine n is like oscillating or whatever because the denominator just gets so much bigger. So what we want to do is basically, sort of replace this thing in the numerator with like a constant effectively. So the way to do this carefully is to say, actually, this is still kind of like scratch work, I guess. So here's our scratch work. We'll say, 1 plus sine of n over n, absolute value if you want, is less than or equal to 2 over n, right? So here's the key, right? You want to make sure that you're moving in the right, like the really common sort of error to make here is to accidentally try to make this expression smaller and you end up with like, so you could say, okay, it's bigger than like 0 or something, or I don't know, like it's bigger than, who knows what, like 1 over a million and 1,000 n squared for large n. This is probably true. I mean, I don't know. But my point is just like any of these like smaller expressions are useless to us because they don't say anything about what this is doing. The point is if we come up with a bigger expression that we can still control, then by making this expression be small, we can make this one be small too, right? So basically, here's our sort of approximation, right? 2 over n. And then we can say, okay, we want 2 over n to be less than epsilon. That's basically like saying we want n to be bigger than 2 over epsilon. So we could take 2 over epsilon to be our capital N, right? So that was kind of all, I don't know, this is all kind of like separate. So pick n to be 2 over epsilon. Then for n greater than n, so, Sn minus 0, which is equal to 1 plus sine of n over n is less than or equal to 2 over n, which is less than epsilon, because n is greater than 2 over epsilon, right? So that's basically it. Are there any questions about that? So hold on, let me bring the chat back up. Or the participant list or whatever. Okay. So the important thing to take away from this is that this was kind of still a relatively simple example of how you can take complicated expressions and kind of fudge them, manipulate them and just turn them into different things and do it in a way, in this careful way of so that you always increase the value of the expression, right? This was bigger than this one. And you also make it simpler until you get to the point where you can just easily bound whatever expression you're looking at, right? This is still a relatively simple example of that, but it's the same basic process. No matter how complicated this got, you could have 5 terms on top and 7 terms on the bottom, and all you have to really do is just kind of find ways of fudging each of the different terms on top and each of the different terms on the bottom until you end up with something that's a ratio of some powers of n or something like that, right? So there's a kind of a general pattern of simplifying expressions this way by just kind of messing with them in a way that always makes the value increase, right? Okay, so if there are no questions about that, I think we can go ahead and move on to a question about sort of another proof. So let's see. Yeah, actually, I'll just clear everything. So here's another thing. Prove the limit of, oops. So I don't know, let Sn be a sequence. Prove the limit of Sn equals 0 if and only if the limit of the absolute value of Sn equals 0. Okay, so I'll just go ahead and put you guys back into the same little groups, and you can take another 10 minutes and we'll come back. Okay, so the um the proof itself here is actually very simple. In fact, I would say that it's it would pretty much be enough to just say that you know, Sn minus 0 is less than epsilon if and only if. By the way, this often stands for if and only if. So and then if and only if, right? Because these two are actually just equal, right? This is just Sn and this is just Sn. So basically, right, one of them is within 0 from or within epsilon away from 0 if and only if the other sequence is within epsilon away from 0. But let's, just for the sake of practice, I just want to quickly kind of go through like what this proof would look like if you wanted to be really thorough and like kind of pedantic, uh, and really, dot all your I's and cross all your T's, as I like to say. So we would say first, suppose Sn converges to 0, right? Then because of that, now let epsilon be greater than 0. So now we want to show that that the absolute value of Sn approaches 0, right? Then there exists an n such that for all n greater than n, right? But then since we see right, so this is just like one half of it. Actually, I won't even go through the other half because you'd basically just, sort of flip this around. You'd suppose the absolute value approaches 0, then there exists an n such that, and you could put an absolute value in here, but then these two things are equal, so this is also true. So yeah, I'm just being kind of like a bit verbose about this, but the reason that I wanted to do that is just to show you guys again, like to lay out the structure of like how these arguments work. For one thing, because it's an if and only if, that means there are, technically speaking, right? Technically speaking, there are two proofs you have to do. You have to first suppose this one is true and then show this one's true. And then you have to suppose this one's true and show that this one's true, right? So that's one thing. And then the other thing is just like, if you have as a hypothesis, sorry, I feel like I have to sneeze. As a hypothesis here, we have that Sn converges to 0, then we like, the way you kind of leverage that is by, now we need to show this one converges to 0. So we let epsilon be greater than 0. That's like the epsilon we want to get this one to be less than. And then you invoke the convergence of this sequence to find this capital N. And then like in the future, there'll be like similarly structured problems, but where you have to do more stuff with the capital N that you get here, right? Because the relationship between the two sequences will not be as straightforward. So are there any questions about that? That was actually I think it was a relatively straightforward problem. So now here's a sort of a not tricky question, but it's an important thing to be aware of. Actually, I'll just clear again. So let's see. Oh, weird. My whiteboard is like messed up. All right, whatever. So here's a question. So question. If the sequence absolute value Sn converges, does Sn converge? And I'm not going to put you guys in groups. I just want you to take like 15 or 20 seconds to think about this. Okay. And then and then I'll maybe, see if anyone wants to try to answer. But yeah, on your own for just a little bit, just think about it. Okay, so would anyone like to take a stab at answering this question? Yeah, Rahul?
I said no because like sine of x exists and absolute value of sine, I guess technically. Wait, no, it doesn't, huh? Oh yeah,
Not
but
quite. Although you're on the right track. You're definitely on the right track.
there exists something where there is a function where I know that for sure.
So one other
sine was a bad example.
Sean Ack, would you like to try?
Yeah. The example that I thought of was -1 to the n, or
Yeah. That's probably like the simplest example of a sequence that does this. So yeah, it's like sine, it's oscillating, right? But yeah, it's like so yeah. So the answer is no. Right. Then in this case, absolute value of Sn is just 1 all the time, right? So Sn, absolute value of Sn converges to 1, but clearly Sn itself does not converge. Very good. Okay, so we have a little bit of leftover time. I think what I want to do is, let's see. Actually, yeah, let's do one more like group problem. I think we have time for this. So let's clear everything again. So maybe we have time. I'm not sure. It might be a little bit hard, but we'll see. So let be a bounded sequence. So there's a number m such that the absolute value of Tn is less than m for all n. And let Sn be a sequence that converges to 0. Show Sn Tn also converges to 0. Let's try that. So I am going to, let's put you guys back in the groups. Okay, so let's wrap up here. Let's do this. So let's think, right? Okay. Let's think about how our proof is going to go. So we want to show, right? So we have all these hypotheses. We want to show that Tn approaches 0. So that boils down to, like, you know, we want, that boils down to picking capital N such that Sn Tn minus 0 is less than epsilon, right? If we let epsilon be greater than 0, that's at the very beginning, obviously. So we want to make this be less than epsilon, okay? So we want to get a handle on how big this can be, right? And so there are two things here that we kind of have to control, right? One of them is Tn, which we have an upper bound on that. So that's how we can control Tn. And then we can use the convergence of Sn, you know, which converges to 0 to control how big Sn is, right? So first, note that, I mean, I guess you could consider this scratch work, but Sn Tn is less than or equal to m absolute value of Sn, right? That's because of the upper bound on Tn. So so now we just want to get this to be less than epsilon, which would be the same thing as trying to make Sn, absolute value of Sn, be less than epsilon over m, right? So pick capital N such that Sn is less than epsilon over m, right? Then, oh, this is for all n greater than capital N. Then for n greater than capital N, we have Sn Tn is less than or equal to m absolute value of Sn is less than or equal to, you know, m times like epsilon over m, right? Which is epsilon. So then we're done. Does anyone have questions about this? Again, you know, there are these sort of common themes that will recur over and over again of, you know, leveraging convergence of a sequence, right? By intelligently picking sort of like we picked this upper bound for the absolute value of Sn, and then with the intent of like applying the definition of convergence to say that we can force absolute value of Sn to be less than this number, right? So we kind of came up with this number separately, but by looking at what we wanted in the end and saying, okay, you know, if we can get this overall thing to be less than epsilon, that would be like, you know, getting this thing to be less than epsilon over m, and we can do that using the convergence, right? So that process just happens a lot. Yeah, so if there are no questions, then I guess we can call it a day.
Oh, are you not a fan of using the little box at the end of proofs?
Oh, I mean, I don't have a strong opinion about it. Like,
Okay.
sure, it's nice, you know. It's just in an informal setting, like, you know, I just do whatever, really.
Okay.
Yeah, sure, we can say, yeah.
Cool.
Yeah. All right. So yeah, good. I'll see you guys tomorrow. Yeah, have a nice evening.
Thank you so much. Bye.
Thank
Bye-bye.
you.
Thank you. Thank you.
Okay.